quarter vanadium, that is which is nothing but gate 91. So he is going to share with us the glimpses of the various aspects of welding of P91 today. And he is also a well-known trainer internationally. So we are really lucky to have him today to share the knowledge on P91 with us. Over to you, Mr. Pradeep. Quarter vanadium, that is which is nothing but gate 91. So he is going to share with us the glimpses of the various aspects of welding of P91 today. And he is also a well-known trainer internationally. Yeah, over to Mr. Pradeep Goswami.
Yeah, thank you very much. It's my honor to be, it's my honor to present this lecture in front of such a a large audience, although it is virtually. But leaving aside that, it's really an honor, and I would definitely thank IIW for giving me this opportunity. As for myself, Dr. Krishnan and Mr. Chinoy has already given a brief introduction. So I'm in this area for as a welding and metallurgy profession, in this area of welding and metallurgy profession for last 37 years. So having seen quite a bit of materials, quite a bit of, fabrication, welding, material selection and corrosion and, service life related issues. So there are a lot of things to talk about, but out of many things, I chose this topic because P91 is a challenging material to any metallurgist or any welding engineer for that matter. And definitely what I have seen, what I have learned and what I have gained over the years, I try to share some of my knowledge base as well as the recent developments in this field, latest developments in this field with respect to this alloy. And I hope you'll find this presentation as quite interesting. So I would like to start now.
Yeah, you can share now.
You are the host now, you can share your screen. Yeah, we can see the screen.
Yes.
Just make it full screen. Yeah, okay.
So I hope you're all of you are able to see it clear.
Yeah.
Yeah.
Okay. Yes. It's nice thing. It's my pleasure to present this in front of you. So going into the presentation, today's presentation would be on the welding of CSEF or CSEF, that is creep strength enhanced ferritic grade 91 steel, practical aspects. So under this part, the presentation overview will encompass introduction, design advantage, various accepted specifications, chemical composition, heat treatment conditions, manufacturing routes as followed in the mills, transformation behavior, welding consumables, specification procurement conditions, metallurgical conditions, considerations for welding consumables, the effects of various alloy elements, then preheat, interpass temperature, welding and post-weld heat treatment condition, post-weld heat treatment requirements as per various codes of construction.
Pradeep, could you increase the screen size so that we can see a little more clearly?
Better
Thank
now?
You. Better.
Okay.
Thank you, sir.
Okay, thank you. ND and inspection requirements and few case studies, and at the end, the conclusion. I try to, give a broad profile about this alloy so that it helps everybody to understand what this alloy is, how it came in, how it came in the industry, and then we'd like to move forward. So about the introduction of this alloy is now have a worldwide application in the fabrication of supercritical boiler, heat recovery steam generators, and as well as for pressure vessels. It has excellent mechanical and high temperature properties, and these are the solid design basis of this alloy. This alloy, as a matter of fact, was originally developed by the Oak Ridge National Laboratory for heat transfer tubes in the fast breeder reactors in late 70s. And as probably if you know, or as a matter of fact, this project was later cancelled. However, the fossil fuel industries were feeling the need of some materials which would have allowed them to operate the plants with higher degree of reliability. So they decided to embrace this material for headers and high temperature components in boilers, and later in piping also. So as a result, the ASME Section 1 code adopted this material in 1983 under the court case 1943. And from that point onward,
sorry, can I request you to just press Control L so that it becomes a full screen? Right now we are seeing the Adobe screen as well. If you could just press Control L.
Control
L.
All right.
Yeah, now it's a full screen. Thanks so much. Sorry to disturb you.
Thank you. Okay. So from that point onwards, basically, this material once it was adopted, or once it was accepted by ASME code, it gained very broad experience for high temperature components in both power and petrochemical industries. Now, this slide is about the design advantage of this alloy and what's typically designer's perspective. Here is a brief comparison of this alloy versus the conventional alloy, what we call as P22, that is 2 1/4 chrome 1 moly steel, which is extensively used in any power plant as well, any high temperature related applications. So as you see out here, a choice between when a designer chooses between P22 to switches from P22 to P91, there is approximately as close as 54% wall thickness reduction, which is definitely an attractive option for as far as any heat transfer is concerned. And on the right, you see that a typically forged component, right? When you talk about an F22 versus F91, you see that there is approximately 65% savings in the weight. These are typically the design considerations under the fossil fuel fossil fuel plants. Typically, what you see out here, the pressure is as high as 4,000 psi, and the temperature is as close to 550 degrees centigrade, which is pretty high. So you see out here that there is a considerable savings in the material, which is an attractive option for any designer. But always an attractive material doesn't mean that it is, it is very attractive as well as welding and fabrication aspects. We'll go to those later. So definitely once the P91 came in the market, many industries where the high temperature material or suitability of high temperature material was a concern, they jumped onto this alloy. And gradually that got accepted. A lot of things, a lot of fabrication histories, a lot of failures, a lot of things were established, but somehow those helped to establish this alloy's credential in the industry. So going to the next slide, what we see out here is what I've tried to present is the various accepted specification, chemical composition, and heat treatment conditions. This is a brief snapshot of all the specifications, which are used or which are adopted for P91 material. This slide also is on the same thing, except that it tells about the typical heat treatment conditions as well as the mechanical properties, typical mechanical properties one can expect. Now, one thing to note is that actually these slides, what I'm showing here is pre-2019, but from 2019 onwards, various sections of ASME codes have allowed subtle changes in the chemistry as well as heat treatment conditions of this alloy, which I'm going to describe, which I'm going to talk about in the following slides. Now, what happens is that nowadays, as far as from 2019 onwards, what ASME did is that all sections of ASME code classifies grade 91 steel as either as type 1, type class 1 or class 2. Now, this class 1 or class 2 division or classification is based on the final heat treatment typically. So type 1 steels are typically normalized and tempered. Type 2 steel is quenched and tempered. Now, in the next few slides, I've tried to extract the salient mechanical properties, heat treatment, and other chemical composition, and for the pipes as well as for the plates. So for the pipes, the referred specification is SA335, and for the plates, it is SA387. So when you see the 335 SA335 pipes, these tables are extracted from ASME section 2 part A. When you see under P91, there is type 1 and type 2 alloys, and the nominal strength, mechanical strengths are as highlighted. And there is a catch out here, the heat treatment condition. The heat treatment for both both type 1 and type 2 are normalized and tempered or quenched and tempered. And here what you have is the normalizing temperature. That means basically this temperature is, when the material is in the mill stage, at the forming stage, for normalizing, the alloys have to be raised to this temperature. And after these, they have to be typically, air cooled and tempered later. And if it is quenched, then definitely they have to be, liquid quenched. And after they undergo normalizing as well as quenching and tempering, this is the recommended subcritical annealing or subcritical tempering temperature. And you see out here, this is 730 to 800 degrees centigrade. That is recommended by the code, ASME codes. So here is a typical chemistry of type 1 and type 2. The difference between type 1 and type 2, there are some certain minor differences with respect to chemistry also. When you see these, when you see the normal alloying elements, carbon, manganese, phosphorus, silicon, chromium, molybdenum, you see that they're almost back to back. They're almost the same. But when you see out here on the residual, so-called the residual alloying elements, you see here that the type 2 generally has a lower nickel content as compared to type 1. Aluminum is the same, right? But here it talks about there is one ratio called nitrogen is to aluminum ratio. It should be typically more than 4. Generally speaking, type 2 is recommended for application where generally the creep and enhanced, high temperature properties are more of a consideration. That means there is something of a category like supercritical and subcritical boilers. Now, subcritical boilers, if somebody wants to use P91 material, the choice would be type 1. But if it is a supercritical boiler, typically the designer has the flexibility either to go on a type 1 or a type 2, okay, depending on the specific design considerations. So on the same note, let's see what the plate says, what is specified for the plate materials. Plate materials are used for pressure vessels, typically. In the boilers also, they're used for the headers, etc. If it is fabricated out of plates. But here, what you see out here is that generally for the plates, only they're available in class 2. Now, for the plates, the class 2 is typically the normalized and, normalized and above, the normalized and tempered grades. So basically, you see out here, there are type 2 is differentiated from type 1 by requiring a restricted composition for enhancement of the creep strength. Now, typically here, what you see that grade 91 steel has got different similar temperature mentioned about austenitizing as well as for tempering. And here, actually, I wasn't able to put this slide, I had to put it horizontally to, accommodate all the materials, all the chemistry here. So here it tells about typically the composition for plates for grade 90 for type 1 and type 2 steel under the specification S387. And this table talks about the tensile requirements for the class 2 plates, and you see out here is that grade 91. This is the typical recommended mechanical properties as per the code. So up till now, these few slides gives the typical mechanical conditions, typical conditions of delivery, as well as the heat treatment which the steel would require before it is delivered to a fabricator's shop. Let's look at have a quick look at the manufacturing routes followed in the mill. Generally, basic oxygen furnace or BOF is very commonly used for grade 91 steel. Following the manufacture, it goes through special steel making processes like dephosphorization, ladle refining, and as well as vacuum degassing. Each of these processes helps to cut down the gaseous as well as the metallic and non-metallic impurities, as well as so-called the tramp elements like sulfur, phosphorus, arsenic, antimony, etc. in the steel. So all these processes produce clean and homogeneous steel. The basic oxygen furnace and ladle refining limit the inclusion of tramp elements, as I mentioned earlier, of elements like arsenic, tin, antimony, and assure low phosphorus and sulfur contents. So here is a typical manufacturing route for the steel. As you see here, starting from the steel melting process, then it goes to ladle refining, then it goes through the degassing process, then it goes through the ingot pouring or ingot pouring, and you see here after the ingots are poured or cast, right? They undergo they're shaped. Following shaping, then they go into the slabbing mill where they're rolled into typically, say, like plates. And after forming to this product to plates, they undergo something called sizing as well as the rolling, right? And this rolling is quite critical because it allows to get the plates, it allows the plates to achieve the required thicknesses as per the specification or as per the client or as well as the vendor's requirement. Following rolling, the plate goes the final heat treatment. This heat treatment is very critical. That is typically the normalizing and the tempering cycles which were mentioned earlier, that is delivered onto this final or finished product. And after this heat treatment is done, or after this phase of heat treatment, the various mechanical tests which are called by the code as well as the manufacturer specification are done for this material, and then it gets delivered onto the product to the end user's door. Now, with respect to this steel, there is a severe, there are specific concerns with respect to the transformation, cooling rates, and hardness level. P91 is a martensitic alloy. Now, martensitic alloy, generally speaking, when you talk about this, when you utter the term martensite, then always people get a shiver, saying that, well, martensite means something which is very strong, very hard, very brittle. But that's not the reality. The beauty of martensite is that, yes, martensite is something in the so-called metallurgical term, martensite is a distorted microstructure, but martensite gives, when the martensite is properly tempered, it gives a beautiful combination of strength, toughness, as well as other mechanical properties also. So that was the concept, or that was the beauty of P91 steel. So as you see out here on these graph, you see here that the vertical line is the temperature, and the horizontal line are the typical cooling rates. And here you see that this is faster cooling, and you go on to the slower cooling because you are increasing the time allowed for cooling. So with the faster cooling time, generally speaking, you are able to get martensitic structures at the at the room temperature. And when you go for typically slower cooling, it's a mixture of ferrite plus carbide, which makes the steel quite soft. So you see here that a very well-cooled martensitic structure before tempering can have a hardness of 400 to as well as 390. This is typically in Brenel, right? But when it is cooled very slowly, you can have a hardness level which could be as low as 180 to 150. Which is definitely not the right grade of P91 material. But having said that, if this alloy is properly cooled, if this alloy is thoroughly taken care of, it could give a hardness in as cooled condition from 400 to as well as close to 400 Brenel or equivalent number in beakers. Now, let's go to the next slide. Just a quick recap of it. And you see here is that there is something called MS, or martensite start temperature, and there is something called MF, martensite finish temperature. This MS and MF, these two temperatures are very critical for this alloy. MS is for this steel is as high as 400 degrees centigrade, whereas the MF is as low as 100 degrees centigrade. So that means from, say, like the welding, and this is a typical CCT, continuous cooling transformation temperature curve for this alloy. So that means typically from the welding temperature of, which is definitely over 1000 degrees centigrade or so. When one is going through a continuous cooling process and hitting this martensite start temperature and allowing the steel to cool to 100 degrees centigrade or below, and getting a hardness of close to 400 degrees Brenel, getting a hardness value of 400 Brenel or more, there are something called a continuous cooling process, and definitely this MS and MF temperature are critical things one has to keep in mind, and that definitely will figure when it goes through welding as well as subsequent heating and cooling cycles. I'll talk about those later. So this section deals with the welding consumables, and I've tried to capture the specifications, various specifications, metallurgical considerations, effects of alloying elements, welding consumables, and some data sheets as example. And critical consideration, that is a nickel plus manganese, as well as other aspects of ASME codes. So this table is a quick presentation about different type of welding feelers which are used for this alloy. This is the TIG, or gas tungsten arc welding. This is the stick or shielded metal arc welding. This is for submerged arc welding. This is for flux core arc welding. Now you see here, actually, this classification is what is shown here is B9. Actually, this was a this slide, this table is a bit old, honestly. Now this specification has got changed to 91, which I'm going to talk about later. But this is a quick snapshot of different type of consumables and their nominal chemistry. With respect to the grade 91 steel, there are huge number of alloying elements involved. Let's see what are the typical role of each alloying element. First, start with the nitrogen. It increases the as you see here in front of your screen, it has got all good effects. In a way, it increases all the tensile and mechanical strength, but has a little effect on ductility. Lower toughness is due to the formation of nitrides and other elements. It has influence on the creep rupture strength by formation of carbonitrides. This is a very important aspect. This is a very important constituent with respect to the creep strength. Typical nitrogen content is allowed is 0.04%, and recommended aluminum is to nitrogen is around 4% maximum. Now, next is niobium. Niobium is needed to maintain the creep properties. It lowers toughness though, but that's why the maximum niobium content is approximately 0.05% typical, and generally above that there's a dramatic loss of what you call Charpy-Notch test, Charpy-Notch values. Silicon greater than 0.15% reduces the toughness. But silicon is a good deoxidizer, and definitely it is needed for deoxidation and for prevention of porosity. Typically, maximum silicon content of 0.2 to 0.3% is acceptable and allowed for this alloy. Carbon decreases toughness, but 0.08 is the minimum content required for the creep strength. Vanadium is a very critical element in this alloy, because the general nomenclature for this alloy is chrome molybdenadium steel. So vanadium is needed for creep properties, to enhance and to maintain the creep properties. However, the content greater than 0.25 significantly lowers toughness. So that is why a typical vanadium content is 0.2, or vanadium is kept between 0.2 to 0.25% typically in this steel. Nickel plus manganese. Manganese and nickel have got influence on strength properties. Nickel increases toughness. As you know for sure that it's a very common element where toughness is needed for any alloyed or stainless grade of steels. But with respect to P91 alloys, nickel has a nickel has a good role to play, but it should be under control. So that is why the code specifies typically that the nickel plus manganese content should be controlled to a maximum of 1.2% to avoid the lowering of AC1 temperature. AC1 temperature, in fact, is the lower critical temperature. Manganese to sulfur ratio, as you see here, that typically manganese to sulfur ratio greater than 50 do not exhibit crater cracking phenomena, which is combined with the low phosphorus content. So manganese and sulfur ratio basically is needed. Manganese is an element which generally takes or binds with sulfur to form manganese sulfide. And it helps one way it helps to keep the steel clean and keeps the tramp elements under control. Oxygen content. This is a critical aspect or critical part of these alloy. Generally, lower oxygen is beneficial for good or satisfactory toughness. With respect to the oxygen content of TIG, shielded metal arc and flux core arc welding, the content may vary typically from 100 for TIG, 300 to 700 for SMAW, and typically 600 to 1000 ppm for flux core arc welding. Flux core arc welding generally is a common process, but when it comes to the notch toughness, frequently we see that the flux core arc welding do not perform to the extent, a TIG or a shield stick or sub-arc welding consumable, as good as those consumables. So one reason for that is generally flux core arc welding consumables or weld deposits typically have higher level of oxygen. GTAW or gas tungsten arc welding metal gives a superb toughness compared to all other base metals, and generally that is the rule of the game, or those are some of the rules for choosing the welding consumables of this alloy, for this alloy. Now, low hydrogen is a must, because this steel is very much prone to any form of cracking. Hydrogen cracking is a very common consideration. So H4 category for shielded metal arc welding is a must. And for subarc fluxes, also the wear flux combination, it should be typically H5 category. So nitrogen is to aluminum ratio should be typically 4 or more. And this is a key requirement for type 2 grade steel. As I mentioned earlier, that's the grade which is more needed for elevated creep strength requirements. And it says that it's also stated that lower ratios than stated above were found in to be the reason for formation of aluminum nitride, resulting premature failure. That came out of the experiences which the thermal as well as various types of industries had faced over the years. So that is why that is why after taking a look at various failure histories, ASME around 2019 or so decided to fix or decided to control this ratio as far as these P91 alloys are concerned. And but if they want to make this but they didn't want to do it as just all across the board. So that is why they kind of classified this alloy grade 91 to type 1 and type 2. And type 2 alloys, as I mentioned earlier, has got this restriction. So coming back to these welding consumables, this is a quick snapshot of what the ASME Section 2 Part C talks about the welding consumables for these alloys. What I have shown here is the extract for shielded metal arc welding consumables. So as you see here, it talks about that. It talks about the MF from martensite from finish or temperature, and it talks about that manganese is to nickel content and their effect on the post-weld heat treatment temperature. So in a nutshell, what happens is that basically there are certain rules which has to be followed or which needs to be followed for for the base metal as well as welding consumables. And definitely these are the key things which one has to keep in mind while choosing this alloy and going for the fabrication and subsequently to move forward. With respect to as I mentioned earlier, nickel plus manganese content is has got a very crucial role for this steel. So as you see here, this is the graph which was developed by Metrot, typically with the help of EPRI, Electric Power Research Institute, back in the 80s, right? And as you see here, the dotted line is the curve for P91, and this firm line is for P92. We'll talk about this P91 alloy. So you see here, prior to 2019, the maximum nickel plus manganese allowance for this grade of steel was 1.5%. So based on 1.5% maximum, you see that the AC1 temperature used to be in the range of 760 to 770 degrees centigrade. And that used to be the maximum limit for post-weld heat treatment temperature, which the industries were, asked to follow. Later, after looking all the pros and cons, after looking at the difficulties, right, they decided to restrict this alloy, this nickel plus manganese to 1.2% maximum, and typically 1%, you know. So when it is between 1 to 1 and between 1.0 to 1.2%, one gets an AC1 temperature close to 780 or more, above 780. We'll see the next slide. This is taken out of API 938B, right? It says typically, it shows that, I've tried to plot these lines, with respect to the various nickel plus manganese content. And as you see here, when it is 1% nickel, the AC1 temperature is close to 800 degrees or a little above 800 degrees centigrade. When it is 1.2%, the AC1 temperature is approximately 790 or so. When it is as per the older rule, that is as per the earlier rule, that is 1.5% nickel and plus manganese maximum, this AC1 temperature was of the order of 780 degrees centigrade. So typically, when the alloy, this content is controlled to between 1 to 1.5%, the mills, the fabricators, they get an additional allowance of 20 to 30 degrees centigrade with respect to the maximum tempering or maximum post-weld heat treatment temperature, which is quite significant with respect to many properties, many problems, which we'll talk about later. So going, just staying in this slide, I hope I have tried to make it clear exactly what are the different, what are the typical AC1 temperatures at various levels of nickel and manganese content one can expect. Now, the following slide is it shows the cooling pattern of this alloy from the typical melting or the pouring temperature. And as one can see is that it goes through liquid plus delta ferrite at very high temperature, then followed by a very wide range of, austenite, as you see here. And from that austenite, it is just from upon cooling, it is going to a temperature, it is going to a typically martensite as well as some residual delta ferrite issues. These delta, these delta ferrite issues typically doesn't come much in the weld metal, in the welding consumables, but when this alloy is formed to other shapes, like if they're forged or if they're cast, then based on this pouring temperature and as well as the cooling rate adopted, there are cases or there are instances of some residual delta ferrite in those alloys, right? And definitely those have an effect on the various metallurgical properties, especially the toughness of these alloys. So that is why casting and forging of involving P91, they are difficult to weld in many instances than the formed products like plates or pipes. These are the quick snapshots from different consumable manufacturers, from the product book. So this I extracted from the manual or from the product catalog of Metrod. So it talks about their products, about typically what are the microstructure one can expect, and what are the typical post-weld heat treatment conditions, and what are the typical preheat and interpass conditions or interpass temperatures recommended. Actually, this was, as you know, this 1.2 or 1% nickel plus manganese content, this is very recent. It was in 2019, it was around 2019. So still many of the welding manufacturers, they still keep these, their product catalog still reflect these maximum 1.5% for nickel plus manganese. But leaving aside that, if you consider, about the post-weld heat treatment and various other properties, they almost remain the same. And these are a quick, another snapshot on these alloys, on these welding consumables. As you see here, typically they are H4 category, and these are typically they are typical, the chemical composition. And you see here the typical nickel plus manganese is 1.3%. One can expect from with this brand. And these are typical mechanical properties. And you can see here that hardness as welded, it could be 450 Vickers, right? And hardness after post-weld heat treatment, it could be 250 Vickers. And this is the number, 250 or so, which the fabricators should aim, after all good fabrication practices and, for following the rules of the code and the specifications. I'll go to that later. So in the same note, these are the continuation of the mechanical properties as well as difficult composition. Different compositions. So you see here that Metrode can give you nickel the same consumable, the grade 91 consumable, in less than 1% manganese plus nickel content also. So with respect to that, there is this is the snapshot from another reputed manufacturer, that is Voestalpine, or who were earlier known as Böhler Thyssen. So this is typically, you see when you talk about these manganese plus nickel, as per their catalog, it is 1.4%, but it could be less or so if the manufacturer, if the fabricator wants, but they have to go back to the consumables manufacturer for that aspect, to fulfill that aspect. This is another Metrode, Voestalpine or Böhler product. So you see here, this is another consumable, Böhler Fox. And here you see that the manganese plus nickel content is typically 1.1%. So going back to the manganese plus nickel limit, let's see what the different codes talk about that. I have tried to present here the restrictions imposed by 4 different codes. ASME section 1, that is typically for the boilers. And next slide is on B31.1, that is the piping, which is our the steam piping. Next slide is B31.3, typically the process piping. And the next slide is typically ASME section 8 DIB 1, which is applicable for typically the pressure vessels. Now, as you see here, these alloys are classified as P15E group 1 with respect to ASME section 9. And the nominal post-weld heat treatment temperature, which is recommended by the code, is 705 to 775 degrees centigrade. As you see here, there is a very wide range, wide allowance. And when you go to the next, when you go to the other, what do you call it? So, sorry, this is for B31.1. And when you go to that section 1, that is the boiler code, it is also 705 to 785. And when you go to B31.1, it is 705 to 775. B31.3 piping code, for the process piping, it is 705 to 775 degrees centigrade. And for section 8 DIB 1, they talk about the minimum holding temperature, 705. And they do not talk about the maximum holding temperature. They don't tell it outrightly, but they tell it later, subject to certain notes, as I have highlighted here. So as you see here, there are lots of ifs and buts. And probably if I start talking about each one of them, it's going to take the whole day to narrate everything. So that is why I decided that to prepare a kind of a quick spreadsheet. As you see here on the spreadsheet, you see the code, minimum, post-weld heat treatment, maximum, nickel plus manganese, how much it should be allowed. And this is for section 1, B31.1, B31.1, and you see here you're able to see yourself that what are the typical minimum and maximum post-weld heat treatment temperatures, and what are typically the nickel plus manganese content, which is allowed by the individual section of these codes. And same here is 31.3. This table is for 31.3 and ASME section at div 1. Incidentally, you will see that piping code B31.3 and B31.1, they think alike. That means basically, excuse me, basically what you will see that an uniform level of specifications are allowed by two different code committees or by two different codes, but they're same. They're basically same, almost word by word. ASME section 8 div 1 is a bit different, but coming back to these nickel plus manganese content, the general summary is that it should be typically less than it should be typically between 1 to 1.2% maximum, as the latest requirement, or as per the latest specifications, or as per the latest ASME code requirements. So up till now, we probably have covered quite a bit of information, shared quite a bit of information on these alloys, on this alloy. So let's see the next part of it. The next part of it are on typical fabrication aspects or typical fabrication problems. Now, many of you definitely have seen this graph or typical graphs applicable for grade 91 steel. I mean, when you see here, this is typically the welding cycle, and where the preheat and interpass temperature is generally, the preheating is, first part is the preheating. The preheating is typically typically up to preheating is up to 200 degrees centigrade, right? And from that point onwards, it is once the welding is started, this is the interpass cycle. Typically, the interpass cycle is maintained between 250 to 300 degrees centigrade. Once the welding is complete, from this point onward, the alloy has to be cooled down. And this has to be a slow cooling cycle. And this cooling down has to be definitely, this is 100 degrees centigrade, where as you see here is the MF, or martensite martensite finish temperature. So 100 degrees centigrade or below. And it says here that the cooling down to the ambient temperature after welding, that ensures complete martensitic transformation. Typical MS temperature, martensitic start temperature is 400 degrees centigrade, and MF martensite finish temperature is 100 degrees centigrade. So from all aspects, it is recommended that this alloy should be preheated. A very strict interpass temperature should be maintained, and after completion of welding, it should be cooled down to the ambient temp or the room temperature at a slow cooling rate. Now, once it is at the ambient temperature, this particular cycle or this particular time frame, that is the time, that is allowed to do any kind of inspection or NDE on this alloy. Now, many time it happens that this is too short a time to do any kind of ND or inspection on these alloys. So vendors may think that, okay, let's do a full ND or QA activity after the post-weld heat treatment of this. We'll talk about that later. But generally, from good manufacturing or from good quality assurance point of view, there should be one ND step at this temperature. Now, from this temperature onward, the alloy has to be heated to the post-weld heat treatment temperature. That is typically 780 degrees, typically nominally 780 degrees centigrade, and or it could be below also, at a typical nominal heating rate of 80 to 100 degrees or 80 to 120 degrees centigrade per hour. And following the soaking of 2 to 4 hours, typically, depending on the section thickness and depending on the design code, it has to be slowly cooled. Oh, what happened? It has to be slowly cooled to the room temperature. So that means basically what we see here is that recommendation is that preheating, welding, martensitic transformation, ND, QA, post-weld heat treatment, and then final cooling to the ambient temperature after post-weld heat treatment. It should go in one full or one complete or one continuous cycle. Now, somebody may say that, okay, why not break it up? We'll see, we'll talk about those later, what could be the complications and, what are the difficulties one may face. So this is again, here I've just tried to capture the continuous cooling diagram and the post-weld heat treatment cycle side by side. So just for, better understanding. So that means basically when you talk about the cooling rate from the welding temperature, well, after welding, that is following welding, if one is cooling this alloy to the ambient or room temperature, one can expect this level of hardness, typically 400 and above, okay? 400 and above in beakers, I would say. And so coming back to these fabrication issues, let us, I have tried to put a few points here. The previous slides illustrate welding, illustrates following welding, why the weld should be cooled immediately to the ambient temperatures. Grade 91 steels are capable of developing thorough martensitic structures in relatively straight sections, that is plate, pipes, and tubes. Actually, there's a spelling mistake here, sorry for that. Martensitic transformation, when tempered properly, results in the best combination of mechanical properties, that is tensile strength, notch toughness, hardness, as well as the best grip strength. Hence, immediate conventional cooling, non-forced, right, to ambient temperature after completion welding is desired. MF, martensite finish temperature for this grade is approximately 100 degrees centigrade. Hitting this temperature range by slow, that is natural cooling, is essential during welding. Sorry, I missed this term. Missed this word. Castings have different cooling rates based on the sections and possibly hence possibly of mixed microstructure. There's a possibility of mixed microstructure. Ferrite carbides or bainites does exist. Then let us see what the APRI, Electric Power Research Institute, they did quite a bit of work on these alloys. Their recommended practices say. It says that following completion of welding, the temperature of the component shall be reduced, to 175 degrees centigrade. Basically, this is respect to typical case studies, but he says that the critical part is this one. The component shall be maintained at a temperature of 80 degrees centigrade. The component shall be stored in a humidity controlled environment to ensure that no condensation occurs at any time prior on the OD or ID surface prior to post-weld heat treatment. We'll talk about that, why it is required. Why it is required. This is typically what are the different preheat, interpass, and dehydrogenation treatment required recommended for this steel. Now, with respect to this steel, there is a term called dehydrogenation or DHT, or post-weld bakeout. Now, as I mentioned earlier, sometimes the fabricators may not be in a position to do or to perform post-weld heat treatment immediately after welding. Now, under that case, what the fabricators should do? It may be risky, considering the fact that the welds have something like a 400 or even anything above 350 or 400 vickers of hardness. What is recommended is that as a minimum requirement, a DHT should be done, or post-weld bakeout should be done. The DHT basically facilitates the hydrogen diffusion from the weld. Typically, a 4-hour bakeout at 250 to 300 degrees centigrade is a recommended practice for SMAW, submerged arc, and flux core arc welding. For GTAW welding, for full TIG welds, it may be reduced to typically at 250 degrees centigrade 1 hour. That is because of the fact that GTAW consumables typically they have very little or almost zero hydrogen in the weld deposit. Here, right. So, going back to that, to summarize, what we have seen up till now is that, as I stated earlier, or as I shown earlier, this is the recommended welding cycle one needs to follow. If everything is perfect, everything is in order, if all the variables are under control, then this typical welding cycle is desired for fabrication of this steel. And if we, as following the good fabrication practices or good welding practices, if we are able to follow this cycle, definitely we are kind of, I would say that we are maintaining the good engineering practices as far as this alloy is concerned. I have tried to, with respect to post-weld heat treatment, the post-weld heat treatment is a very critical issue for this alloy. I came across this materials and welding forum is a very popular forum for welding, discussions related to materials and welding issues. Sorry about that. Few years ago, I came across a query where one gentleman had asked this question. You can see it yourself. He says, "Dear experts, in my site, we conducted a demonstration of post-weld heat treatment on grade 91 material. It was 70 millimeter thick. As our client requirements and details are given as given below. This is the typical heating and cooling rate client insisted. This was a typical holding temperature. And this was typical the holding or soaking time, the heating bandwidth and insulation bandwidth, everything was specified. The heating method was induction heating. During the post-weld heat treatment, we observed a temperature difference on outside and inside of the pipe that was more than 80 degrees centigrade. Now, the problem was that the client was not accepting this method and was asking for uniform temperature in and outside and inside of the pipe. His question was, how can I control temperature on both sides? Is it possible to have an uniform temperature on both sides with induction heating? Please give your valuable advice in this matter. I'll come to this topic in the next few slides. With respect to local post-weld heat treatment, we follow, or AWS-D 10.10 is a very very common and very popular specification or guideline which is followed by the industry. AWS-D 10.10 describes induction heating as application of alternating current to coils wrapped around the part to be heated. Electric current has an associated magnetic field, or a magnetic field is produced around the conductor. The magnetic field penetrates the part around the component where coils are wrapped or placed. Now, commonly used induction frequencies for post-weld heat treatment for the pipes are typically 60, 480, and 9600 hertz. This is a very, this is a typical frequency which one comes across, as well as, when induction heating is concerned. Ferromagnetic steels, that is grade 91 steels, tend to contain all of the magnetic properties within its wall thickness. Carbon low alloy and other ferritic steels are ferromagnetic below their Curie point, the point at which the metal are no longer ferromagnetic, which is approximately 770 degrees centigrade. This is very close to the AC1 temperature of grade 1 steel, grade 91 steel, that is 700 to 800 degrees centigrade. And they are non-ferromagnetic above this temperature. Now, what happens is that induction heating versus post-weld versus resistance heating, these two are these two methods are followed conventionally for local post-weld heat treatment of these alloy. That means if you're doing the post-weld heat treatment in the field, these two methods are used. Induction heating has sort of, it is a catchword. It has taken it has just come up pretty fast over the last few years. But it is fast, it is accurate, it can do the job in no time. But one sort of, I would say that one problem area, or one of the drawbacks of this alloy, of this method, is this Curie point, where the alloy turns to, P91, which is a ferromagnetic alloy, just gradually turns to non-magnetic when it is exposed above this temperature. But that doesn't mean that induction heating cannot be done. Induction heating is a popular heat treatment method, and it is adopted by the industry. But what may happen is that if this alloy, say like by any chance, needs to be heated to 800 degrees centigrade and above, there may be possibility of formation of something called hot spots. And that may cause some, invalidation of the post-weld heat treatment process. So one has to keep that in mind. Here is a typical post-weld heat treatment method, which is the is a local post-weld heat treatment method. This is typically the post-weld heat treatment cycle, which is followed for this alloy. And as you can see out here, this is a typical input supply for induction heating. And here is a demonstration of induction heating. I took these photos out of a paper which was presented by Mr. C.N. Kumar of BHL Bangalore. It is in this Fab 91 seminar. So what you see here is that these coils are externally wrapped, and these coils could be water cooled as the thickness and as well as the temperature goes up. And you see the typical heating, so-called the temperature lines inside this. that means the coils are wrapped outside, but there is something like a reddish line or a temperature zone inside. So induction heating is quite popular for this alloy. So popular is the conventional or resistance heating also. And these are the post-weld heat treatment methods followed for, other than I'm talking about the furnace heating, these are the post-weld heat treatment methods followed for these alloys. And both are popular, both has got its pros and cons. So a fabricator has to judge the best technique and then adopt the technique followed by, meeting all the specifications or all the technical requirements. Now, with respect to this induction heating or post-weld heat treatment by induction heating method, generally it is a recommendation to standardize or to qualify the equipment as well as the process through a mock-up. Many times it is not written in the specification, it is not written in the code book, but that is basically the mutual or reciprocal understanding of the fabricator as well as the end user or the client. And since post-weld heat treatment is an absolutely important critical phase or critical step in fabrication of these alloys, qualification of a post-weld heat treatment process definitely considered essential. So up till now, I think I have run through quite a few of the things. Let's jump into the NDE and inspection requirements. Grade 91 steels are generally acceptable, they respond to all conventional all conventional NDE techniques, visual, MPI, radiography, ultrasonic. Those are and as well as the PMI or positive material identification. Those are frequently used or those are regularly used, and those are mandated by the design and fabrication codes for fabrication and ND, for ND and quality assurance of these steels. And definitely, without a good ND or inspection protocol or inspection regime in place, getting a defect-free, welded product is not possible. So that is why all these ND techniques has to be evaluated, and they have to be standardized, they have to be evaluated and duly accepted, and then only they should be put in practice. In the next few slides, I have tried to cover a few case studies involving grade 91 base metals and welds. Case study number 1. It states a 3-inch section pipe under thermal blanket heating, preheated at 150 degrees centigrade, interpass is 250 degrees centigrade, process stick as well as TIG and flux core arc welding. Immediately after the welding, after welding, the spool piece was wrapped and cooled under covering, not steel air cooled to the room or ambient temperature. Question is that what could be the consequences? Here are some of my thoughts. Grade 91 is a crisp strength martensitic stainless steel. The purpose of heating to 100 degrees centigrade or further down to room temperature after welding is to ensure any austenite formed and retained during welding would fully be transformed to martensite before post-weld heat treatment. Otherwise, this retained austenite can be transformed to fresh martensite upon cooling from the post-weld heat treatment temperature at which is typically 770 to 780 degrees centigrade. Hence, steel air cooling of grade 91 steel is a technical requirement. Look also look at slide number 44 for illustration. So slide number 44, which I have, all of my slides are numbered. So you can look at that slide for illustration. That is typically, the CCT, or the continuous cooling diagram, or continuous cooling transformation slides for this alloy. Typically what happens is that, is that cooling to the 100 degrees centigrade or further down is kind of a rule of thumb, or kind of a sort of a absolutely essential requirement for this steel. Case number 2, a 3-inch pipe section, thermal blanket heating, preheat at 150 degrees centigrade. Interpass is 250 degrees centigrade. Process is TIG stick, as well as TIG plus flux core arc welding. Immediately after welding, the spool piece is properly cooled to 100 degrees centigrade and then to the room temperature, 30 degrees centigrade. Vendor wanted to delay the post-weld heat treatment, as wanted to get a furnace load of spool pieces, which is a deviation from normal good practices for fabrication of P91 steel, which could be, I would say. The vendor decided to perform a stage ND, preferably automated ultrasonic, and the results were found to be acceptable. Final ND as per the QA plan was after post-weld heat treatment. What should be done meantime, as the post-weld would be delayed? Answers: few possible solutions. Apply DHT, dehydrogen heat treatment, at typically 300 to 350 degrees centigrade for 3 hours, for at least about 3 hours at least, typically 1 hour per inch basis. This should be done in spite of the fact that typically H4 and H5 consumables are used for stick as well as flux core arc welding process. Avoid any condensation or ingress of the moisture inside the spool pieces or on exteriors. This could cause SCC, or stress corrosion cracking, as moisture condensed water could be acidic and may contain atmospheric pollutants. As welded hardness of the girth seams could be easily 350 to 400 HV with little ductility, hence the spools loading and unloading shall be done very carefully. Post-weld heat treatment should not be delayed beyond 48 to 72 hours, typically, as a rule of thumb. Now, with this part, many of us may not be aware of these consequences of any kind of condensation or moisture, and typically condensation of these on these steel which are not post-weld heat treated. But industry experiences in North America has shared these as delayed post-weld heat treatment followed by the ingress of moisture or any condensation on the steel as the root cause of so-called the SCC, or stress corrosion cracking, for these. There have been some case studies or some interesting findings on delaying the post-weld heat treatment, but without taking much precaution, delaying it typically in a humid climate. These are typically some case studies on the continuation of the case studies. This is a case study of P91. This happened in 2007. It went viral in the web after its failure. It shows typically a steam pipe, basically a high temperature steam pipe. It kind of just sheared through the middle. As you see here, it just sheared through the middle. Well, there were a lot of hue and cry after it happened in this place. And there was a kind of a investigation, and these were the findings. This failure occurred in a P91 approximately, of 1.6 inch or 1.7 inch, that is over 40 millimeter thick walled seamless pipe. This pipe was not considered to be genuine. This was later thought to be a counterfeit. A pipe was operating at something like 1006 degrees Fahrenheit, which is close to 540 degrees centigrade. The failure occurred in the vertical section and was away from the weld, almost 86 inch away from the nearest weld. These are the typical rupture sizes, 35 inch by 1.5 to 2 inch. I'm talking about this length. This was the typical length of the rupture. These were some of the findings or some of the facts which the so-called investigations had established. There may be a bit of controversy involved, so that's why I'd like to I'd like all of you to take a look at it. But at the end, it was declared that these pipes were something like fake pipes. And what is it meant by the fake pipe is basically that these pipes didn't have any manufacturing history. This pipe probably didn't come from the right mill, or they didn't come from the right stockist. They didn't have a good traceability, or they didn't have any, as I mentioned earlier, manufacturing process and quality history. So the rule of thumb is that when, it talks about how a P91 material can, what sort of a manufacturing deficiency P91 or grade 91 material can have. When buying this material, it is an absolute necessity to know the mill, or to know the stockist, or to have a good manufacturing history, and then only procure. I would say that way, but many a time it happens that there are always deviations of the rule. Issue is that if somebody wants to deviate, then definitely this deviation would be at, deviation from good engineering practices always involves some risk. So one should kind of judge the risk and then only do the deviation. But other than this, I would say that it is very essential to know the so-called the source, manufacturing place, manufacturing history, and the subsequent processing and subsequent track of this material before it lands in your shop. This case study is on the typical failure of a component, a header cap in service. And as you can see from your photographs, that basically this is the component, right, which is shown here. And basically the failure was just like a wide mouth failure, which went propagated right through the entire thickness of the weld. As you see here, generally, and this was, this was the pictures or the snapshots taken on the exterior of the weld, which shows typical cracking at the toe of the welds. Now, generally speaking, this kind of end caps are recommended or are accepted by ASME Section 1 code, but in the case of piping, or I would say that for Section 8 Division 1 pressure vessel codes, they kind of, they do not accept this kind of end caps outrightly. Rather than a flat end cap, I would think that an end cap which is the shape of a typical cap, I would say, would probably have been a better design. But anyway, this is accepted by ASME Section 1 code, and this kind of design is followed in many boilers and and the boiler headers. And typically this kind of a weld, this kind of a weld configuration is prone to failure in many instances. Section 1 code has a lot of histories about it, but always what happens that, I mean, one can overcome these failures by good engineering practices, but many times what happens that every good engineering practice cannot be incorporated in the code. But having said that, this happens, and this happened in a utility. This happened in the utility environments. So basically, these are the root causes. So established, what it said is that the poorly designed weld joint pipe to end cap, which influence so-called the type 4 region of the weld heat affected zone. Now the type 4 region basically is a creep type. Typically creep is a high temperature deformation, high temperature degradation of any alloy, or in this high temperature environment. Type 4 creep is a creep, is a sort of, I would say that is a range of creep in the creep deformation curve, which is beyond, which is beyond repair. Basically, type 4 creep, once the type 4 creep has set in any weld or heat affected zone, definitely that's basically the death warrant of that component. That means it will progress and it will fail at any point of time. So the presence of the narrow strip was a degraded soft material, possibly the end cap side. And this was confirmed by the hardness analysis as well as the fractography studies. So the various deficiencies have led to a number of premature failures, such as the complete separation of the end caps from the headers and through-wall capping of pipe to stop valves after less than 5,000 hours of operation. So 5,000 hours are nothing, right? In the context of any utility. Subsequent actions and improvements, operator utility implemented comprehensive baseline inspection program during the design and modification stages, which were able to detect many of these deficiencies before further failure. What does it imply is that basically, as a result of this end cap failure, the utility rather woke up and started inspecting every end cap or the major end caps in this header or the supercritical section of this plant. And they were able to isolate many of these end caps. And as a matter of fact, they did the due diligence, either replacement or repair over a period of years. And there was something like an industry-wide alert, which sort of alerted the other utilities also to do the same. This is another P91 failure, and it says that if superheated tube at a subcritical boiler, it is a subcritical boiler, not a supercritical boiler, failed after 25 years of service, which is fairly, I would say that it had done its own part, causing a forced outage. The tube was a grade 91 steel, which is a typical 2-inch OD and typically 5 millimeter or 6 millimeter of wall thickness. And here, what is shown is the failure pattern, or the close-up view of the failed superheated tubes. And these are the hardness profiling, or these are the very hardness readings taken at the various failed section. So as you see here, at different locations, when you take the average hardness, the hardness readings were, I would say, between 230 to 276 Vickers, which is nominal, which is typically nominal for this grade of steel after complete fabrication. But failures can happen, and in this case, having seen that the failures failures happened after 25 years of service, which is fairly reasonable, I would say. And what happened was that it was found that in something, this tube was repaired or something called pad welding. Pad welding is a very common phenomenon which is followed by the boiler industry. What happens is that if there is a minor leak, they will just do a sort of a repair pad or repair patch And you see out here, this is the area which was pad welded. Sometimes that works, sometimes that doesn't work. It is just like you have something like you got a minor leak and you try to glue that leak with a pad weld. That works for typically carbon steel and low alloy steels, but not the way it should have been done for grade 91 steel. But anyway, this pad welding was done, and later this pad welding failed, and this tube was ruptured, and that caused a forced outage in the for that utility. And these were the typical creep voids or the creep deformations noted around the around the welded and the fusion lines. These are the typical creep micro voids. That means what happens is that creep. Assume this is like a creep crack. This will not happen abruptly. It doesn't happen overnight. It just creep failure happens over the years. And typically over a period of time when there are all these micro voids created by this deformation, right? High temperature deformation, they tend to join up and then lead to this form of creep crack. That's an altogether different phenomena, different subject, and but in a nutshell, to say that this component failed due to a faulty welding practice, which is the pad weld, and basically it happened after prolonged exposure in the creep, in the creep transformation or creep deformation temperature range. And subsequently, they found that and they decided to stop this pad weld or repair practice for this alloy in years to come. And some of the, I'm almost at the end of my presentation. I would say that these are, I tried to show some of the typical fabricated products which are made from this alloy. And as we see out here, these are typical headers. These are main steam pipings. I've extracted this from a presentation of West Alpine or Bola Thyssen, which was done a few years ago. And these are typically the steam headers of any of a coal-fired or fossil fuel power plant, and this is the main steam piping of a coal-fired power plant. You see the year 1989, 1991. That is quite a bit of premature. I mean, that was a time when industry had just adopted this material. Whatever restrictions, whatever chemical issues, chemical composition, heat treatment and all these issues, which I narrated in my earlier slides, many of them were not there. But still industry wanted to go ahead with this alloy. There were many failures, lessons learned, and because of these failures, lessons learned, there were tons of improvements in design, engineering, and fabrication practices involving this alloy. So this is another photo of a typical, we call by welding engineers term, it is a dreadful component, which can have a dreaded consequences. Because here the welding involves a main steam pipe, which is typically, it could be anything close to 3 inch or so, depending on the design and design temperature and the pressure involved, to a forged weldolet. And you see this is the groove, and this is a typical weld buildup or weld deposit. And the extent of welding can be enormous. And so basically, this is typically show the thick walled weldolets on a main P91 steam pipe. Welding process was shielded metal arc welding. As I stated earlier, due to extremely high volume, extremely high weld metal volume configurations, such welds cool very fast and may require a 24/7 welding schedule and careful QA monitoring. And typically for these weldoliths, one has to be very careful about this toe cracking, which is very common for these for failures down the road from many industry experiences. But this is a common design which is adopted by ASME B31.1 code. And when there is welding of these weldoliths to main steam pipe is concerned, one has to be extra careful because of the shape, and the group size, and the ultimate, you see the weld volume involved. So to summarize, these are some of my conclusions. Grade 91 cannot be treated in the same vein as just like another chrome moly steel. This alloy requires considerable care during joining to assure complete long-term properties. When utilized in the proper manner, grade 91 alloy show exceptional performance at elevated temperature applications. Continued use and premature failures will reinforce the fact that the detailed design oversight, quality assurance, and as well as the welding practices are absolutely necessary when employing this material in any sort of capacity. The previous slides narrate some of the suggested good practices with grade 91 steel. Irrespective of the service environments involved, good engineering practices are absolutely essential while handling this alloy. So that ends my presentation, and I would like to thank all of you for your attention for over last 1.5 hours. I hope I have been able to, kind of enforce or kind of send the message to everybody with respect to fabrication practices or with respect to design, selection, fabrication, quality assurance of this alloy, and definitely what happens that good engineering practices at the design and construction stage helps to prevent abrupt failure as well as any kind of fatalities or any kind of unwanted consequences in service. So I would like to thank IIW for giving me the opportunity to present this webinar. And at the end of it, I'd like to thank all the audience concerned. Hope you enjoyed this presentation and look forward to meet you in, I look forward to meet you in future also. Thank you.
Thank you so much, Pradeepji. We have got close to about 70 questions for you, and there are many more which have been put in the chat box. If you can spare some more time, we'll request Dr. Krishnan to pick a few, and then we can email you the rest for your answering.
Oh yes, I see that there are yeah, absolutely 70 questions. Yes.
And I would like to mention there were about close to 250 people who were live all this time, and just up till about another 10 minutes ago, we've now got a strength of more than about 180 still there. So thanks a lot. It was really wonderful. And I would ask Dr. Krishnan to jump in quickly and take some questions with Pradeepji.
Yeah, Mr. Mr. Goswami, there are almost 70 questions. I think you would like to pick a few from that. Is that fine with you?
Yeah, I can. I'll try to scroll through and answer as much as possible.
Yeah.
The first question comes from Gerald James. It says, please give some comparison between 91 type 1 and type 2 steel with respect to the allowable stress values with respect to ASME section 2D. Section 2 Part D and applicable boiler codes. I would say that basically, with respect to that, you have to go through ASME Section 2. ASME Section 2 typically gives the stress values. There are individual tables and for each alloy under each specific code. So from there, you can choose what's the typical allowable stress values. And if you have any issues, you have my email, you can write to me separately, right? But as to answer to your question, I would say the comparison is available in Section 2, and as well as individual design codes like B31.1 or B31.3, as well as ASME Section 1 also. But to summarize, Section 2 Part D is considered to be the general stress. That gives the summarized stress values with respect to all individual codes.
Yeah, the next question is regarding comparison between P91 type 1 and type 2 steel. It's, I think, again on the allowable stress part with respect to 2D.
Oh, yes, absolutely.
Yeah, so moving on, we can take one question on from Mr. Ghosh. It says the current code for ASME requires nickel plus manganese to be less than 1% for longitudinal welded fitting. Is there any specific reason for the same?
Yes. Actually, what happens is that this 1.2%, less than 1% is for these fittings are the best materials, right?
Yeah, right.
These fittings are the best materials and they are welded. Now, what happens is that if you are able to, and subsequently, and following the welding, mind you, any welded product has to be tempered, or any welded product has to be stress relieved. So if you're able to keep the nickel manganese to less than 1%, at least you're able to do the tempering of these fittings at a slightly higher temperature. At least you are able to do this at a temperature close to 800 degrees centigrade or so. So that gives you some additional safety with respect to the subsequent fabrication. That means what happens is that if you're doing the tempering of these, or if you're doing the post-weld heat treatment of these fittings at that 800 degrees centigrade or so, at least you are having some extra cushion. And that is the way I would think that the code tries to play safe.
Yeah, right.
And so what happens is that, say like you have a pipe or you have a fitting, right, which was tempered at a higher temperature than what you are going to follow in the final fabrication. Then what happens is that if that less than, with nickel and manganese being less than 1%, if you are able to get a good mechanical properties, at least you're able to avoid something called softened P91 fittings. That means what happens is that generally these fittings, typically what happens over the industry experience is that fittings often give you something like a hardness, very low hardness, less than 200 Brinell. There have been cases like that. So the idea is to keep it under control to ensure a good, I would say the good tempering, as well as to prevent unwanted soft fittings which being used or which being kind of dumped onto the fabricators, and which could be a problem down the road.
Right. We will move on. Yeah, we have a very interesting question on the dissimilar welding. So suppose I have to weld a P91 with a say austenitic stainless steel or with inconel, and which filler wire is being recommended as a good practice?
Where is that? P91 to
Austenitic stainless steel, as well as suppose it's an inconel pipe.
Yeah.
This question is by Mr. Gaurav Dak at 605.
Okay, so the issue is that it is P91 to austenitic stainless steel or Inconel 600.
Yeah.
Yes, it's a DMW dissimilar welding is a, I mean, very burning issue, I would say.
Yeah.
Yes, I mean, some rule of the I mean, there are a few rules, I would say. In this case, it is a, it is a welding between P91 and an austenitic alloy. Austenitic alloy doesn't require any post-weld heat treatment, whereas the P91 always require post-weld heat treatment. Generally speaking, if I'm going to do post-weld heat treat an austenitic alloy at that high temperature of close to 750 degrees centigrade or so or more, that's not good for this alloy. So given a choice, I would insist that this post-weld heat treatment can be avoided. So the best effort should be to butter the P91 with an Inconel. It could be Inconel 82 or Inconel 182. 82 is the TIG wear, and 182 is the stick electrode.
So it is ERNICR3?
EINICR3 or ERCRNIFE3.
FE3.
So it should be buttered. P91 should be buttered. Then subsequently it should be post-weld heat treated. And the thickness of the buttering should be at least 5 to 6 millimeter after machining or grinding. And following post-weld heat treatment, any austenitic consumable, any austenitic 300 or Inconel shall be welded to P91. And the vendor may use the same Inconel 182, Inconel 82 consumable, which was used for buttering.
Right.
Well, I would say that in that case, there are different school of thoughts. And I've seen many answers where people say, oh, let's just do the welding, right? I mean, why bother about the post-weld heat treatment? But my approach is that, yes, the post-weld heat treatment is definitely to be avoided for austenitic product. And in that case, buttering and post-weld heat treatment and subsequent welding is the best solution. Yes.
We move on. There is one question from Mr. Ashok. Is site welding of P91 feasible? If so, what extra care would be needed if it is unavoidable?
Where do I see the question?
Well, I am picking up random because we have.
Oh, okay.
Yeah.
All right. See, the issue is that site welding, whether it is site welding or shop welding, P91 has to be treated like P91. It is difficult. I know that under site welding conditions, it is often quite difficult to adopt the best welding practices for this alloy. But you need to do whatever best is possible. So it should start from right from the material control. Right, how you get your material, how you store your material, right? It should start with the consumable procurement, consumable storage, right? And subsequently it would percolate, or it will go down to the fabrication practices also. So effectively, whatever best is possible, you should. My answer is that you should try to prepare a spreadsheet or a checklist of whatever are the critical steps and whichever are the best or whichever are absolutely essential for his trouble-free site operation, and accordingly you should try to move forward. But to make the story short, P91 requires special care, and absolutely under the site welding condition, one has to enforce that. And you need trained and experienced QC as well as welding engineer, as well as a good set of welders, to control all this.
Yeah, Mr. Goswami, we have another question from Mr. Sagar. It's a very, very common question which we come across in the sense, generally, these materials are used for very high temperature application. Okay, but if you see some of the specification, they still ask for toughness testing.
Yes.
The question, why is it mandatory to do a toughness testing in the PQR?
I would say it is mandatory. I would say it is mandatory. Why? Let me explain. As I mentioned in my presentation, right, there are many alloying elements, and all these alloying elements have got a good effect with respect to toughness. Like when you talk about alloying elements like nickel, manganese, nitrogen, right? All these have some positive effects on toughness. As far as this steel is concerned, this steel operates in a very, demanding environment. They operate in, typically in a, they operate in the temperature regime of, I would say, the 1,000 to 1,200 degree Fahrenheit, or something like 550 to 600 and 650 degrees centigrade, right? Yeah. Which is a very high temperature for this for what do you call for any material. The failure modes are typically the creep. Basically creep deformation or creep failures are very common. That's why these steels are called CSEF, creep strength enhanced ferritic steel. Now, what happens is that the good creep property is to a certain extent linked to your toughness also. Because after all, creep failure, to delay a creep failure, the material has to be tough. Number one. Number two is that many of these plants are, it doesn't happen in India, but in the West, in many instances, these plants are exposed to cycling. Okay, what does it mean by cycling is that, say like today at 6 o'clock, the so-called the energy board or the grid operator will say that we don't need any power. Then the utility will decide to abruptly shut the plant. And maybe 24 hours down the road, again, the utility will get a call that we need power. Utility has to wake up the plant abruptly. Now, what happens is that this thermal cycling, we call this as thermal cycling. This thermal cycling has got a very, it is very tough on this material. They cause something like in addition to the creep failure, there is something called a fatigue failure also. Okay, so to cut the discussion short, I would say that basically a good toughness values, a good toughness is one of the key parameters to kind of mitigate these damages down the road. So that is why, irrespective of the fact whether it is a high temperature application or not, toughness or notch toughness is a requirement for a procedure qualification test, and typically it should be plus 20 degrees or in that range. There is no need to go for sub-zero toughness test, right? For this steel or for the welds also.
Yeah, I think EN code has plus 20 degrees for this material.
I would say that plus 20, plus 30 is generally the rule of thumb.
That is a safe bet. Yeah, moving on. There is again a question on welding between grade 22 and grade 91. So the question is, what is the reason we choose B3 or B9?
Yeah, there are two different school of thoughts, right? some designers say that basically B3, 22 and 91, there are two different alloys. 91 is a martensitic steel and 22 is a typically ferritic steel. There are differences of properties as well as differences of operating conditions also. So typically there are two different school of thoughts. Some design requirements say that you may use B3 or you may use B91 consumable. If you choose B3, then your welding criteria, acceptance criteria should be based on the failure, based on the mechanical properties of P22 alloy. That means what happens is that when you have a dissimilar coupon, that means one side is grade 22 and other side is grade 91, and it is welded with B3 consumable, then it would undergo the post-weld heat treatment requirements of a B3 consumable, not grade 91 steel. And following that, when you do the mechanical test, basically the load or the so-called the failure, the stress at which the failure is occurring, the acceptance should be based on the grade 22 plates or the B3 consumables for that. On the other side, you may use B9 or B91 consumable also, but in that case, you have to use the post-weld heat treatment cycle for B91, which is typically 750 degrees or so or more, depending on the design and fabrication code. That may cause some kind of softening or tempering of the grade 22 base metal and the heat affected zone. So that's I would say that's a little bit of negative side of choosing a P91 welding consumable. But a designer, depending on the availability, depending on the design code, you have the flexibility of qualifying a dissimilar joint using both type of welding consumables. And if you choose B3 or the issue is that whether you choose B3 or B91, you should stick to the recommended post-weld heat treatment cycle for that consumable. Does it explain?
Yeah.
So.
And another, there is a practical problem, it seems. P22 and T91 combination welding. If hydrogen crack occur, how can we repair? This crack propagates after completion of repair procedure, then what to do? So it's between P22 and T91.
Question is that is it after fabrication or after service?
It is after fabrication. There is a hydrogen crack.
Well, I would say that in that case, if it is happening immediately after fabrication, after post-weld heat treatment, one has to be very careful about that. In that case, the repair has to be done. And generally, the thumb rule is that for this steel, industry or end users generally do not permit more than 2 repairs.
Right.
So one has to be very careful about that. And if it is noted, then definitely we have to kind of remove those crack, repair that crack. And once you repair that crack following the original welding procedures, you need to follow the same post-weld heat treatment or same welding cycle. So, and you have to be very careful to follow all the due diligence and basically to ensure that this crack doesn't come back again. And once you have adopted good engineering practices like those, possibly you should be able to get over this issue, unless there are issues related to the parent material. So as I said earlier, that knowing the parent material history and the supply, its carbon content or its alloy, alloying content is heat treatment. Basically, what I'm saying that knowing the history of the material is very important. And if you are able to ensure some, what you call, simulation test, right? Maybe at your own expense. If the mill doesn't do it, you may do it at your own expense also, right? Then you know for sure that whether these extended post-well heat treatment cycles have got any so-called negative effects on the material or not. But to cut the story short, I would say that if you experience cracking immediately after fabrication, you have to repair that crack, or you have to repair those, you have to resort to a repair weld following the same cycle which was followed in the actual fabrication. That's the only way.
Yeah, correct. So there are large number of questions. I will pick one from the NDT side. Will PAUT without TOFD yield correct result for P91?
Well, TOFD is the general, TOFD or time of flight diffraction is commonly followed for new fabrication. And POUT or phased array ultrasonic is also equally popular. So the fabricator, depending on the availability, one may choose. One can go for the either. I would say that way, but but the qualification of the equipment and the qualification of the operators, those are important. But I have seen that TOFD, TOFD is more popular than phased array in the earlier years, but now phased array is widely popular, as popular or as widespread as POUT, in terms of the availability and the acceptance by ASME codes. So I would say that both the techniques work well, depending on the equipment, depending on the operators, and and the place where they're utilized.
Yeah. Also, your joint geometry matters.
I beg your pardon?
Yeah. What I was telling is also your joint geometry matters, whether it's an
that's right. That's right. That is irrespective of the process. Joint geometry is essential for any. That's an essential part of any weld.
Right, and there is dissimilar welding by GTW process. It looks like a tube sheet where the tube is T91 and the tube sheet is A266 grade 2. That is again carbon steel. So there is some application where the tube is T91 and the tube sheet is carbon steel. So how to do the dissimilar welding by GTW?
You got to see basically what the what is I would say that what is the weld procedure chosen at the first place? I'd like to know basically which filler.
Because I feel we should have the full detail to answer this question.
Yeah, I would also think so. But one is the carbon steel. First of all, carbon steel to P91 looks to be a very awkward selection for me.
Right.
That's number one. Irrespective of the fact that if it is chosen, I would try to go with some consumable which is midway. That mean in that case it should be neither P91 nor carbon steel, but I'll try to stick to something in between. Basically what happens is that here what matters is a tube to tube sheet weld. So T91 to carbon steel, right? And basically I need to choose a filler metal which has to operate at the desired temperature and all. So all those things are important. But if there is a choice, I would definitely not stick to T91, but something intermediate would be a preferred choice for me. But without looking at the details, design conditions, and etc., and all those things, right?
Because
it's not very
yeah,
appropriate to talk about the right answer.
Yeah, because the biggest catch here is going to be what PWST you will adopt, because the tube is T91 and your carbon steel is not simulated for that temperature.
Oh,
So
absolutely.
Yeah. So I think we require more detail. So now moving on, why flame heating is not recommended for grade 91 welding?
Flame heating is, flame heating is not that the flame heating it cannot be done. Flame heating can be done for a smaller component, but the problem with the flame heating is that basically it has something like a thermal shock. But forget about the thermal shock. P91 is able to detect that, but is able to absorb that. Generally speaking, what happens is that for shop condition, if it is a vessel, right? If it is a vessel, then fabricator, and if it is something like a submerged arc welded, right? You have no other option but to go with flame heating. But a lot of these P91 components are pipes and kind of products which are some kind of static. They cannot be rotated unless they're fabricated in the shop. So I would say that for the pipe spools, if they're fabricated in the shop, one may resort to flame heating, but maintaining the temperature, preheating is absolutely essential. But for the site welded condition, definitely where the component is static, it cannot be rotated. Definitely there is no other option but to go for induction or I would say the resistance heating. So coming back to that point, I would say that it's not that they cannot be used or they cannot be recommended, but depending on the shape or depending on the welding process or depending on where it gets fabricated, one may resort to flame heating also. But the flames, definitely one has to be very careful about achieving the uniform temperature, I would say. That's my viewpoint on the issue.
Next one is on again PWST. Can we waive PWST for thickness less than 13 mm?
I would say no.
Yeah, it's a straightforward answer.
Look at the code. Look at the code, what the code says. But typically, for any thickness involved in grade 91, PWST should be mandatory.
Yeah, true. So when this material is operated in the subcritical temperature range, say between 450 to 500, does this allow experience temper embrittlement failures like other chromoly seals like 2-quarter chrome? If not, what would be the reason?
Yeah, that's a good point. Basically, for chromoly steels, typically for the consumables, there is something called X factor, right?
Right.
Which is a combination, which is a typical X factor is a combination of all the tramp elements. So this X factor needs to be controlled for grade 91 steels also. Grade 91 steels generally do not do not experience temper embrittlement because of the fact that the chrome is pretty high, that is 9 chrome, and it contains moly as well as the vanadium. So generally speaking, in that 400 to close to 500 degree range, it doesn't follow. There are not cases reported on temper embrittlement for this alloy. But following the good engineering practices are always essential. And nowadays, all consumable suppliers are able to give the welding consumables with a very restricted X bar values, and we should try to get the welding consumables with those requirements, I would say. But as a matter of fact, these alloys do not face temper embrittlement, which are very common with the chrome, 2/4 chrome on moly steels at that particular temperature range.
Yeah, another one is with respect to the weld consumable. Are there consumables in SMAW or SAW which can give good toughness properties, say at room temperature or at 0?
Absolutely, there are. So that is why whatever those data sheets I presented, included in my presentation, right? Those could be those could provide some useful information, right? Especially if one looks at the data sheet of Metrod, right? I'm not trying to do trying to promote anybody's product for that matter, but whatever was available, I just reproduced it. So Metrod datasheet gives some information. Same is with Thiessen-Bohler also, right? So both are, I would say, the exceptional suppliers of welding consumables for this steel for over 30 years. So one can definitely ask them, as well as the other good consumable manufacturers also, to get the clear answer. So yeah, go ahead, please.
Yeah, thanks a lot. I think we will close the QA session now, and we will compile all these questions and send it to you. Okay, whichever we have not answered, maybe we can send it to all the viewers at a later stage through our website.
Yeah, that would be appreciated. Thank you.
Yeah. So now I request Mr. Malge, Secretary of Mumbai branch, to say the vote of thanks.
Good evening to all. I am Ashok Malge, Honorary Secretary of IIW India, Mumbai branch. It's my privilege to propose vote of thanks on behalf of Mumbai branch. Thank Mr. Pradeep Goswami for having today a lecture on welding 91 grade steels, practical aspects in an excellent way. Sir, with your vast experience, work for 37 years, covered all the critical aspects starting from manufacture of 91 grade steels, ladle refining, desulfurization, vacuum, degassing, etc. The transformation behavior and cooling rates are also covered. Welding consumables, specs, effects of alloying elements, especially the trace elements, including manganese to sulfur ratio, nitrogen to aluminum ratios were also covered in the talk. NDE inspection and requirements. And finally, you could conclude with the case studies which were of really practical use to the most of the audience. The talk was excellent, educative and informative. I once again thank Mr. Pradeep Goswami. My sincere thanks to all participants for their overwhelming response and participating in the tech talk. My sincere thanks to our technical Weld Tech Talk Committee, especially Dr. Krishnan, Mr. Nimesh Shonai, Mr. Abhishek Vas, and Mr. Sachin Surve for organizing this today's talk in an excellent way and make a success event. Thanks to one and all. Thank you very much, sir.
Thank you. It's my pleasure.
Thank you.
Thank you, Pradeep. Thank you. It was a wonderful session, and I think with the number of questions given, you could go on for the whole day. Maybe we'll take this opportunity to invite you one more time in the future when you have the time to spare.
Yeah, it would be my pleasure. Thank you.
Thank you. Thank you so much, sir. Thank you. Thank you, everybody. And it was, let's call it the end of the day. We will share all the questions with Pradeep ji, and as and when he has time, we can share it back onto the session.
Thank you all.
Once again.
Thank you all.
Let's close the session. Yeah.
Thank you.
Thank you.
Thank you all. Bye-bye.
Thank you. Thanks to everybody.
Thank you, Mr. Pradeep. Thanks a lot.
Okay.